What makes black holes so heavy? I get that it accumulates matter and, well, makes it incredibly dense, but what makes them so heavy?
Correct. Next question.
I think we should first start with what is a black hole? Yeah?
So if we talk about black holes, well, there are loads and loads of black holes. And black holes is a really interesting one from a science perspective because
It's a mystery.
Well, it's a mystery, but it's an unraveling mystery. So if you take the last sort of 2-3 decades, thanks to a lot of the cool stuff that we've been able to build and make and stick in space, our understanding of black holes and frankly our awareness of black holes has increased massively over the last couple of decades and will continue to do so. But what is a black hole? A black hole is a super, super, super heavy object, very, very dense object, huge amount of mass. And
with lots and lots of gravity.
Loads and loads of gravity. So there is a black hole in the center of our galaxy.
Supermassive one.
Yeah.
Supermassive, but there are way, way bigger ones out there. There is a big black hole in the center of our galaxy. And the same way that the sun has a gravitational pull.
It's in the center of the solar system.
Absolutely, and the sun kind of holds our solar system together. The black hole at the center of our galaxy kind of does a very similar job, and that's the reason that our entire galaxy kind of rotates and orbits this black hole in the center. If we think about gravity and what makes a black hole so different to, say, the sun or a planet, so what gives something its gravitational force, do you know?
The how tightly the atoms are packed together.
And how many. Yeah. So that it's density and its mass. So if you take planet Earth, it's a huge object. It has enormous mass. Huh?
But it's not very dense at all compared to a black hole or the sun.
Yeah. Relatively speaking.
But compared to you, very heavy. Right?
A great way to visualize this. So if we had a big trampoline in front of us, and so don't think of it as the universe, think of it as literally a trampoline, one of those small ones that you exercise on, or a big one, whatever like trampoline is like. Now, if I got an apple, which has mass and is kind of planet-shaped, and I dropped it into the middle of that trampoline, what is going to happen to that trampoline?
Tiny indentation.
Absolutely. So you're going to see a little curvature of that trampoline.
The trampoline is
centering
space-time?
Where that absolutely. Yeah. So yes, imagine.
So it bends space and time.
Yeah, correct. So Einstein called this. Okay, so here the trampoline fabric in our example, they call this the fabric of space-time. So he took space, the thing that we move in, and time, put them together in something called continuum, and so there's 4 dimensions now. 3 of space, 1 of time, and this is the fabric of our reality, of our universe, right? And it stretches.
So it stretches, so we've got the apple. Now let's take the apple away and replace it with...
A bowling ball.
A bowling ball. A bowling ball that we've squished down. So let's say, an elephant. Let's take an elephant, squish that elephant in something that fits on the trampoline in a sort of spherical way. Drop that in the trampoline. What is going to happen to that trampoline this time?
The trampoline will either fall to the ground and...
For this one, we're going to have to imagine there is a hole in the ground, so the trampoline can stretch as far as it needs to stretch.
It will sink extremely far before
so it curves even more, right?
And what happens, so if you're another object, so if you're a planet, or if I'm going to use the fruit, if you've got the apple there, and I'm a grape travelling across that trampoline, that little curvature that centres itself around the apple, that's going to pull me in. So I'm going to get attracted to that apple depending on how fast I'm going. So with the apple, where we don't have a huge amount of bend, a huge amount of curvature, that grape has a reasonably good chance, if its speed is high enough, of rolling. It may move slightly the way it rolls and rolling off and coming off that trampoline. Now if we take our elephant, we've got much more curvature.
Then
something coming past is far more likely to get stuck, trapped in that curvature, and spin down or fall down and join our squished elephant. Now, if we take a black hole, we take that same thing, you've got the same trampoline. Now let's imagine we've taken the entire planet Earth and squished it down to something about the size of my head. So that's going to be quite hard to lift. But let's imagine we can lift it. And we put that in the middle of the trampoline. So can you imagine now what's happening to that trampoline?
Well, it would probably get bent, but in a very, very thin way.
It would get a very thin way. And right down at the bottom of that curvature, if we take the way that we're visualizing that trampoline, the sides of that curve are going to be pretty vertical. Now, anything that finds its way there isn't going to be able to get out. It is trapped. And that's kind of a black hole has that amount of mass that it affects and impacts the curvature of the trampoline, which, as you rightly said, is the curvature of space-time, to the extent that its trap is huge. So if anything gets too close to the way that's curving, there will come a point which we call the event horizon, and we call it the event horizon specifically for light. So light, that travels pretty quick. So the quicker you're going, the less likely you are to fall in. Now, nothing travels faster than light. But this has stretched and bent curved space-time to such an extent, it's got so much mass, that light travelling across that trampoline, that gets to the point where even the speed that light's going, it cannot escape. It's now falling. So that point where light cannot escape the curvature of space-time, we call that the event horizon. And inside that, once you're inside the event horizon, frankly, we know pretty much nothing. And there's a very easy reason that we know nothing. Because
nobody's been inside and nobody's come out. And
even if you send someone in there, they're never coming out. And even if you sent a probe that could tolerate that gravitational crush, which is very unlikely, but even if it could tolerate that crush, how is that probe ever going to get a signal out of the black hole? Because nothing, including light, is capable of escaping. So that's a black hole in a miniature nutshell.